Hello, everybody. I would like to go through a solutions of one of the questions in tutorial that we do this week. That is the course is UNSW Maths1251. That's a calculus section, and that's a question 6. Now, this is the whole question. It is a long question. This is why I don't want to go through there. It is tedious, but it will be clear step by step how we solve it. So IN is a definition. This is IN, and that is a definition of integral cosine n to the x dx. We know that we've done it last week by using a reduction formula. This one will give you, or another question in your lecture notes, you will see if IN is defined in this way, then we have a reduction formula given by IN n-1 and IN -2 for all n's bigger than 2. So this is, we are not going to show this one, but we are going to use this reduction formula and show this equality and this equality. 2m plus 1 is the odd case and 2m is the even case. And the next thing to do by using this, we are going to show this inequality. Next, by using this inequality, we are going to show that this limit is 1. And we are going to use the sandwich theorem by doing that. Then, by using this section, we will be able to prove that limit of this quantity is pi over 2. This equality is also known as a Wallis product. Then we would like to check by inserting the factor in both cases and for the denominator and denominator in the above product. And we will be able to show that pi over 2 is the limit of this quantity. Now it is long, but let's do step by step. The first thing is we are going to apply this reduction formula consecutively, and we will try to see the pattern and what's going to happen in the end. That's the idea. So for n is equal to 2m plus 1, the first step, we're applying the first reduction. That will be 2m plus 1, n minus 1, your n is 2m plus 1, then minus 1 here, n will be 2m plus 1, and then here we will have 2m plus 1 minus 2 will give us the minus 1. So this is the first step that we use the reduction. Then, now the second, we are going to use exactly the same reduction formula. This time we are going to use for I to m minus 1. Then n minus 1 divided by n, to m minus 1 divided by 2m minus 1. And then we will subtract minus 2 from this quantity. That will be 2m minus 3. So that's the next step. Then if we continue this step up to the end, we will be able to find out I1. 2m minus 1. And next one was 2m minus 2 to m minus 1, which is that guy. And if we keep going to do that, we will be able to get m is equal to 1 is 2, then 3, right? And then 1, that will be 2, 2 minus 1 will be 1. So the last term will be I1. Why this is important? Because we need to calculate the integral defined by I1. So that's the step to do that. I1. So that will be 0 to the pi over 2 cosine x dx. The cosine integral of a cosine is sine, and substitute in sine pi over 2 is 1, sine 0 is 0. Then we obtain 1, plugged in 1. That will give us the first equation that is required. Right? That will be the first equation. We found this equation now. The second equation, which is that one, is exactly the same pattern, same idea, same logic. Then n is equal to m is equal to n is equal to 2m. Apply the reduction formula. That's the reduction formula we are applying again. This time n for us is 2m. That is n minus 1 will be 2m minus 1. divided by 2m, and then minus 2, 2m minus 2. This is the first reduction formula that we apply. Now apply the reduction formula again to this term. Then we will have n minus 1, 2m minus 2 minus 1 will be 2m minus 3. Then we have 2m minus 2, which is n. Then we will subtract 2 from this, which will be 2m minus 4. That is 2m minus 4. If we keep going, applying the reduction formula, this reduction formula step by step, we will end up having I0, right? And when n is equal to 0, cosine 0, the power of the 0 of anything will be just 1. So we have only 1 here. Then taking the integral, we have x, and pi over 2 minus 0, we will have pi over 2 back into the pi over 2 back here. And then this equality that we found, exactly what is required for us to be found, which is that one. It is pretty straightforward, just applying the reduction formula that we have before. Now, the next step, we would like to prove that we have this inequality. Now, I'm not doing anything. I'm just trying to understand first, what are those things, basically. This one is by using a formula. So we have 2m plus 2. Think of this one, 2 out, we have 2m plus 1. So this is an even number. So we can use even number formula. We have two equations that we've just proved. im2 plus 1, I2m. We prove these two equations. So if we put m plus 1 here, we will be obtain another version. So an equality for I to m plus 2. So that's what I do. I put for m is equal to m plus 1 into this equation, and let's see what we have. If we put m plus 1, and so on, organize it a little bit, of course, we have 2, and we have minus 1, so 2m plus 1, and so on. So what is the starting point for us here for this entity? 2m plus 1 divided by 2m plus 1, 2, and so on up to the pi over 2. Why do I need to do that? Because if I prove that I to m plus 1 divided by I to m plus 1 smaller than 1, it is equivalent to show this inequality here. And similarly, I can prove this inequality. If I prove this inequality, then this inequality, it means I proved everything that I need to prove. So this is why I am doing this, right? I am figuring out how can I see as a product of certain numbers, certain rational numbers of this, and what is the product of the this rational number, and then divide them and try to see that this is smaller than 1. If I can prove that, that will be exactly the proving this inequality. That's the idea. Okay, if we divide, we know that if we divide two rational numbers, we will switch the second one and we will multiply that. I think this is clear for you, but let me remind you that if you have a over b and c over d, these are the rational numbers. And if you're dividing two rational numbers, then you will have a over b times d over c. You're swapping denominator and another numerator, and then multiply it. This is what's the definition of how we divide rational numbers. Just reminding yourself, I think it is clear for everyone, but for just in case. Okay, this is as a definition of how we divide the rational number. So this is a rational number, and to m plus 1, and this is a rational number. If you divide it, it means that I am swapping with the denominator and denominator, which is that guy, and I'm multiplying it. And let's see whether some terms will eliminate each other, or I can tidy up a little bit. That's what I want. Okay, there's no term that we can get rid of it from upstairs, downstairs, but we can collect things up So because I have 2m plus 1 here, 2m plus 1, 2m minus 1, 2m minus 2. So it is a square. So I have squares of this kind. And then this one is, if we left it over, and all the others will be squared. And then I have pi over 2, which is not here. So pi over 2 has to be here, and all the other terms will be just a square from here to here, here to here are the same. We are squaring it, and this one, it's a ln, and all the above gives us the squares. Clear? Yeah. Okay. Now, now I would like to prove that this is smaller than 1. And for this, the nature of the question is open for the induction method, because in the induction method, we were thinking about the natural numbers and how we prove induction method, how they prove things with an induction method. We say that we prove the n is equal to 1 is correct, and then we assume induction hypothesis n is equal to k for any k. Assume that one, assume that hypothesis. And then we would like to prove that the next one, which is k plus 1, we would like to prove it is also true by using the previous case. So that's what I would like to do. I would like to use the induction method to prove this. M is equal to 1. We need to prove first one. The first one needs to be true. Something in the middle, we assume that will be true. Just one after that, we would like to prove that it is true. Then it is true for all natural numbers. So that was the idea of the induction method. Just reminding. So m is equal to 1. We have I4 and divide by I3. We're just putting those numbers together. We will be able to easily see that this is 0.8, which is smaller than or equal to 1. For m is equal to k, we assume this is correct. So this is in our induction hypothesis. Now we would like to prove this is true for m is equal to k plus 1. K is a natural number here. So put the k, m is equal to k plus 1. And let's have a look, what are the substitutes we have? I2k plus 4 and I2k plus 3. Now I would like, this is a head term. Now we would like to go back term. We would like to find something times this kind of thing. So we will be able to use induction hypothesis. That's what we want. So how we can go backwards of those ones, how we can do that? Well, we have the reduction formula. We can use the reduction formula. Let's use the reduction formula for the upstairs. So that is the 2k plus 3 divided by 2k plus 4, 2k plus 2. Remember, that was the n over n minus 1, n minus 2. So this is n minus 1 will be n is equal to 2k plus 4 in this case. So that is 2k plus 3. And 2k plus 4, that's n. And minus 2, 2k plus 4 minus 2, that will be just 2k plus 2. I just applied that reduction formula here. What was the reduction formula that I'm talking about? Just remind ourselves again, this one. This is the reduction formula that I'm talking about. I'm applying this one. Yep. And I'm applying the debt reduction formula for this one too, so that I will get something looks like this. Something times looks like that. Okay, n minus 1 will be 2k plus 2 divided by 2k plus 3. So that was 2k plus 3 minus 2, which is 2k plus 1. That's correct. Okay, this part will give me the induction hypothesis. I know that this is smaller than 1 by induction hypothesis, done. But this part, if this part is a positive, if this part is bigger than 1, then I'm done with it, right? Because this is bigger than 1 and this is always smaller than 1. If you multiply that, it will be smaller than or equal to 1. For k is equal to 1, there is that is 1.01 for k is for k is equal to 1. That's I4 divided by I3. This is 0.3. That's I6.I5 is 0.888. And for k is going from to the infinity, this 2k plus 3, this item is going to be going closer to 1. So that means that the whole inequality will be smaller than 1. Similarly, we can prove that the other side as well. So this one will give us I to m plus 1 smaller than or equal to I to m plus 1. And this one will give me that one. Okay, so this gives us the inequality for the second part. It is a bit long process to do it, but that's we prove that this is valid. So once you have, I mean, we don't need to do that again because it's the same process with the one little number, so it will be the same. So you don't need that. Okay, so we prove the inequality. Now we would like to show that this limit is equal to 1. So the inequality that we have, I to m plus 2, I to m plus 1, I to m. Now we divide this inequality with I to m on every side. So the first one here, upper bound, will be just 1. The lower bound, this one will be stay as it is. And okay, the upper one is 1. And lower one we are working on now. So leave this I to m as it is, but apply the reduction formula for the denominator. To m plus 2, so n is equal to 2m plus 2, n minus 1 to m plus 2 minus 1 to m plus 1, which is that guy, and to m plus 2, and then subtracting minus 2 will give us 2m. So that will 2m and 2m will be canceling out. Then have a look to, now we can calculate the limit, because on this side, on the right hand side, we only have a term with m. So taking a limit m goes to the infinity of this quantity will be m goes to the infinite, limit m goes to the infinity to m plus 1 over 2m plus 3. So what this is a rational number, and the coefficients with the same power, right? M has a power 1. This is m has a power 1. So the coefficients is 2 over 2 will be 1. So this limit is 1. So this limit is 1. So what we found, the limit condition on this part, on the lower part, lower boundary part is 1, upper boundary part is 1, then we will use the sandwich theorem. Right? That's what it is here. So the lower bound is 1, upper bound is 1, and the limit in the middle has to be 1. That is by the sandwich theorem that we've seen in our lectures. Okay, then the other ones are just a little bit of substituting it. That's straightforward. Thereafter is straightforward. Now the limit, by using the limit I to m plus 1 over 2m is 1, we know that what is I to m plus 1 over 2m. We work it out with that one, right? Or almost. Well, or easy to figure it out. As you see, the things will come out in this fashion, but this time you will have I to m plus 1 over 2m, and that will give us it's a straightforward to see this. This will be 2m squared to m minus 2 squared up to here, and in the end we will have 2 over n. Since this limit is 1, all of these limit will be just n over 2. Because this is a constant term, I can take this constant term onto the other side. That's straightforward. And this one, from here to here, we just multiply and divide by the same quantity, which is 2m minus 2m squared, 2m minus 2 squared, and 2 up to 2 squared. If we do that, then we will have 2m squared, 2m squared. We are getting all the 2 in one corner. And then we are collecting the similar terms. And then we have m squares, m minus 1 square, m minus 1 squares, and so on, and collecting in one place. And here as well, we have m squared, m minus 1 square, and 2 square. So this will be just m factorial square. That will be m factorial square. This will be 2 square, but m times. And that will be 2 squared m times. So that will be 2 to the 2m, right? 2m, that will be 2 to the 4m. So this will be m factorial square times m factorial square. That means m factorial power of 4. And here we have 2m plus 1 as it is. Nothing it will be done, that one. That will be extra term that we, it's in the formula. And then the downstairs denominator, in the denominator what we have, 2m squared, 2m minus 1 squared, 2m minus 2 squared, that will be just 2m factorial, right? This is a m to m factorial. It started from 2m to m minus 1 to m minus 2, goes down to up to 2 and 1. So that's a 2m factorial, but all of them has a square. So we have the square here. So this quantity is just multiplying this with 2m minus 2m squared and 2m minus 2. It's just looks complicated, but it's really tedious work. That's all for this question. Thank you very much.